Okay, so in this video I'm going to talk about absorption and the basics of this topic, which is a very relevant one because it's about purifying, or let's say removing impurities from gas streams. So this is very common in industry, especially let's say in the oil industry, but it's not only in oil industry. If you think about any processing industry, or many processing industry is better, they produce gases with some, let's say, pollutants, so they need to fulfill some requirements of the law requirements, let's say. So that's why this process is so important. So what's going on here? Basically, a liquid is going to be used. So this liquid is going down, of course, as droplets, and a gas is going to be upwards like this. So if we see what's going on here, a droplet of the liquid is going to be surrounded by the gas, and then some diffusion is going to happen, and the liquid droplets is going to be charged, let's say loaded with some pollutant, and then the gas is going to be free of pollutant. That is what's going on here inside. So there are many things we need to learn about absorption, but I'm going to do it let's say in a quick manner. Okay, so the first thing is that if you have some vapor, let's say gas or vapor, and some liquid, you will have some vapor liquid equilibrium. So if we think about the liquid, so we will say that that's let's say dominated by Henry's law, right? Henry's law. And Henry's law simply tells us that the partial pressure produced by a liquid which is in equilibrium is going to be the molar fraction in the liquid times a Henry constant. And if we think about the gas or the vapor, that's going to be let's say that's going to be determined, or is going to be dominated by, so we have Dalton's law, which is the summation of the partial pressures and stuff, and we can say that as well, that the partial pressure, this is Raoult's law, I forgot the name, but now it came to my mind. So Raoult's law tells us that the partial pressure is equal to the total pressure times the molar fraction in the vapor phase. So we could equal, so set them to each other, we will have this, and this is going to be the equilibrium line or equilibrium curve between vapor and liquid. When we think about this, if we plot, so let's say here we're going to have x and here y, so this could be a line, right? Or maybe no, it depends. It depends on many aspects, but let's say we could have something like this. Okay. The thing is that when we are working here inside, we want to get, we want to, as usual engineers, we want to express this with a mathematical model that is easy to interpret and easy to work with. So we want to work with lines. This is the operating line, this is the equilibrium line. Okay. So how do we make this to be a line? That's the question. So now let's think about this this figure we have here, and let's forget about this equilibrium line for a while, and we we'll be working with that in a couple of minutes. But now what I want to point out is that this is going to come with, so in absorption we are going to work always with some loading. Okay, so what's loading? Loading in the gas, it's going, okay, let's say everything is going to be referred to inert. Okay, so inert is simply, for instance, you have air and you have CO2 and you want to remove the CO2, so the inert is going to be everything that is not CO2. So in this case would be air. And why do we do that? Because the inert is going to be constant in the entire column. So here we will have the same gas inert, same amount, not changed, of course, in the basic case. And here we will have as well the inert of the liquid, the inert of the solvent, let's say, which is going to be the same one here. And that's really amazing because it makes our lives really easy. So here is going to be it's in, here it's out, right? Here we will have y in and y out. Sorry, actually the other way around. Oh, what is this? I believe, yeah, here. Out, of course, and y in. And this is very important. Maybe you are wondering why I'm using the capital Y and the capital X. This is because this is not molar fractions, rather is loading, the so-called loading. So loading, the units of loading are mole of the component we are interested in, let's say component A, over moles of inert. That's why we are using inert here. And the reason is very simple. For me at the beginning it was difficult to get this concept, but it's just because we are going to get a line in this kind of graphs. So this is going to be a line. If we work with y, I mean the molar fraction, this one and this one, this is going to be actually something like more complex, you know, more difficult. Of course, the equilibrium line is going to be a line because we just saw the model here. This would be a line, but yeah, let's say we care more about the operating line. Anyway, so for X is going to be the same, mole of A over mole of solvent. This, of course, is vapor, gas, or whatever, inert in the gas phase. How do we convert from y capital to y, from y lowercase to y capital? Is going to be y over 1 plus y. Easy. And the same for x. So x is going to be x over x plus 1. If we want to do the opposite, it's so x lowercase is going to be equal to, oh, I did double equal here, equal to just y, 1 minus y, and sorry, x, sorry. Anyway, same for y. So this is really relevant, and I wanted to tell you about these units because they are important. Then, if we work with the same diagram now, but in loadings, sorry, x again, xy, we know that the operating line is going to be a line. Why a line? Let's do the balance here really quickly. So let's put a boundary. What is the name of this? It's a volumetric boundary, let's say. I don't remember the technical name now. Anyway, so if we do a mass balance around this, we will say what comes in equal to what comes out. What comes in, very easy, right? So what comes in is going to be n of here everything not just the inner, but everything, right? So let's say n of the gas at the bottom plus n of the liquid at the top equal to n of the liquid at the bottom plus n of the liquid at the top, right? And now if we do a component balance, we will get something like, okay, n of the gas at the, yeah, actually thinking about it, this needs to be inert. Definitely we want to keep this constant in the column, right? So we will do it with inert. So this is inert. Just to keep it in mind, all of them are inert. Okay, so then we will have this times the y in plus nlt, I mean at the top, inert times x in, right, equal to nlb. Yeah, so we get this basically, and after rearranging this we are going to end up with G inert, doesn't matter if it's top or bottom because remember that is constant, times a difference here and n of the liquid inert, this is inert, it's not inlet, inert, okay, times a difference here. So basically it's going to be like so let's say for this one, y in minus so this is going to be, wait, inlet, this is outlet, y outlet, and for x it's going to be its outlet minus its inlet, right? So we could generalize this and just leave it like, okay, we're doing the mass balance at the top of our, or at the bottom, whatever, it doesn't matter. So you just get eliminate. I have eliminated everything, and yeah, that would be general thing. Yeah, and that's the operating line. When you solve for y, you're going to get something like, okay, y is always going to be equal to, yeah, so this is what we get basically. As you can see here, this is going to be like the x value, let's say, and this is going to be the slope of this line, and this is going to be the y-intercept. We could actually change this a little bit and we will get some y-intercept here a little bit different, but that's not actually very relevant. It depends, right, how we want to define the model. But the important thing here is that we have a straight line. And now let's go back to the model that we got here, and that means if we are working in the loading diagram, capitals, we need to change this, right? And changing this would mean y over y plus 1, x, sorry, and this is the total pressure, y over y plus 1. And then if we want to solve for y, we can do it, and we will get some expression which is going to be function of course of x, h, and the pressure of the system, right? So of course we want to get this line in terms of x. This depends on the temperature, and well, the pressure of the system is going to be dependent on the temperature as well and on the volume of the system. But what I want to point out is that the model is not going to be aligned necessarily. It's usually going to be something like this. So when the line is above the equilibrium line, we are doing the absorption, and it's the line where, like here, we are doing desorption. Okay, just keep it in mind. Okay, a very important parameter when we are calculating or when we are designing this type of columns for absorbing gases or traces or whatever is the minimum amount of liquid required. So let's assume we have equilibrium data. I just want to explain the general procedure to calculate that. We are given, because this is a design constraint usually, like we are given how much is going to be the composition at the top of the column. We are going to be given this composition for y, okay, and usually we know the composition of x that is coming here. We don't know this one, and usually we can measure how much is coming here. That means we know in, we know out. Knowing in, out here, this is the top, right? What composition is lower? This one or this one? Of course this one, right? Because this is what we want to get. So we know that we are somewhere like here, right? Lower. So let's say its in is going to be somewhere here and its out is going to be somewhere here. We don't know it usually. And we know y out, which one is going to be higher, this one or this one? Of course this one is higher, right? So we can say, okay, y in is going to be somewhere here and y out is going to be somewhere here. Of course you can see that these 2 points are together. So I mean this point, these two values are together, so we know this is going to be the top of the column, important, at the bottom of this graph, and the top of the column is going to be somewhere here, but we don't know exactly where. Yeah, so how do we get the minimum amount of liquid for this separation? Is going to be something like we know this, and then we know as well this composition, right? I mean, we know this value here. So when this line comes here and hit the equilibrium line, okay, in this case it was just luck that I actually floated till that point, but let's say it's something like going up more to, I didn't know that. So right here we will have maximum or infinite amount of, for minimum liquid or solvent, we have maximum or infinite amount of stages. So what we are going to do is simply to to measure this composition here, okay, which is going to be the maximum or the equilibrium one, which is going to be at the bottom of the column. So when these two streams are in equilibrium, this one and this one, that means we got the maximum high, okay? Yeah, so I was saying when they are in equilibrium, we're going to get, okay, yeah, when these two are in equilibrium, we're going to get the maximum amount of stages in this column. So that's how we can calculate then with the mass balance that we did, which is going to be like here. You know then this out, which is in equilibrium. You know the inlet, you know the inlet, you know the outlet, right? You know this as well, so you can calculate this one, okay? How can you calculate this one, for instance, if you're given total one? So the inert gas is going to be the total one minus the composition of it depends, of course. So you need to think about how to get it. This is one way to get it. Yeah. That's one thing I wanted to say. And usually the real value of that solvent is going to be between 1.3 and 1.6 times the minimum solvent. And then knowing that, you will move this point more or less, let's say here, and then you're going to calculate the number of stages starting from the top or from the bottom. It doesn't matter, but at the end you need to just keep in mind one small concept that I'm going to explain now. So let's say in this case, so if you start horizontally, at the end let's say you don't go up, right? You are going to have to take into account the horizontal distance. So let's say this total distance is going to be a plus b. So you only need this fraction, which is the part of the stage you need. So it's going to be a over a plus b. So total distance, and this is going to give you the total the real number of stages you need there. And if you start at the top, then you're coming here, then you're coming, let's say here, right? Then you are coming, I don't know, here, then you're coming here, and then you are coming here. I mean, this is not very accurate, but what I want to point out is that at the end, what you're going to take into account is the vertical distance, okay? With the one you start is the one that you're going to measure here at the end. I think that's everything I wanted to show you. There is one more thing that it's called efficiency of the absorber. Let's use the same graph now. Let's clean this a little bit. So the efficiency of the absorber is given by this equation, of course capitals, so sorry, which is just the ratio between this and this distance, so equilibrium for the inlet. So as you can see, it is going to be a, it is going to be, the entire thing is going to be a plus b, so a over a plus b, okay? And there is another term that is called degree of saturation. So the degree of absorption is in function of the gas side, and the degree of saturation, which is expressed with this letter, is going to be with respect to the liquid side. So it's going to be something very similar, which is it's in minus it's out. So we have it's in minus it's out here, right? And then we're going to have the total distance again, which is going to be it's in minus its equilibrium. It's in minus its equilibrium. Equilibrium, or simply the star here, the asterisk. Yeah, and that's everything I wanted to tell you guys about the basics of absorption. Okay.